Hello, my name is Aditya Pillai, and this is Lab Report 2, Motion of a Falling Object. Some of the objectives of this lab include observing changes in velocity due to force, comparing computational model predictions with observed data, observing the effects of gravity and drag, and applying key physics concepts. The objective of this lab is to predict the motion of an object while a force is present in order to observe and apply Newton's second law of motion. Some of the concepts applied in this lab are Newton's second law of motion, which states that the net force on an object can be quantified by the object's mass multiplied by its acceleration, the momentum principle, delta p equals F net times delta t, the velocity update formula, derived from the momentum principle, and the position update formula. Two of the fundamental interactions quantified in this lab are gravitational force in the form of weight force, W equals negative mg, and drag force in the form of turbulent drag force, Fd equals negative b times v squared. This is the video in Tracker. Recorded values include the ball's mass being 3 grams and the ball's radius being 4.3 centimeters. The ball travels about 1.4 meters in 0.583 seconds. As you can see, the plot of y over time is parabolic downwards. Another recorded value is the object's initial position at a y position of negative 0.0045 meters. The approximate gravitational force using the weight force equation is negative 0.0294 newtons. From the momentum principle, we derive the velocity update formula as shown. To calculate F net, we set it equal to the weight and drag force. While the weight force is constant, the drag force relies on the magnitude and direction of velocity. From repeated simulation and approximation, we get a drag constant b of 0.001422. The predicted final position without drag is negative 1.673 meters. And as we use the final position to find the drag constant, it is the same as the observed motion. So this is the GlowScript code used for the simulation. Some of the changes to this code include setting the object's mass, setting the object's initial position, setting the proportionality constant and the time frame of the simulation, creating the weight force and drag force equations to calculate net force, setting the velocity update formula and the position update formula, and then setting the aeroscales to represent the forces in the simulation. As you can see, this is what our code looks like when it's run. The graph of the position versus time is parabolic downwards, and the drag force increased as the velocity increased. These are the graphs of position versus time and velocity versus time with the two simulations in the observed video. As you can see, the simulation with drag force was apparently the better simulation as it more closely approximated the observed video, which is especially seen in the velocity versus time graph. However, neither simulation was perfect in simulating the falling object. Before the lab, we were asked two questions. The first question was to observe the velocity versus time graph predicted by the models, with and without drag, and to predict which model would have a terminal velocity. The answer to this is that the first model would not have a terminal velocity because it is a straight line model and does not account for drag force, and the second model that has drag force will, because it is concave up and levels off at some point, meaning that it would have a terminal velocity at some point. The second question is, imagine that the object was initially thrown downwards. Would the terminal velocity in this case be the same or different from the case where the object was initially dropped from rest? So this is what the graph looks like when there is a high initial velocity. As you can see, the drag force drastically increased in proportion to try and level off and counter the initial velocity. Even if the initial velocity is higher, the drag force will counteract the higher initial velocity and bring it down to the level point where drag force is equal to gravitational force, at which point you will find the terminal velocity. Since that point is the same regardless of initial velocity, the terminal velocity doesn't change whether or not there is an initial velocity or not. In conclusion, the simulation with drag force was better at predicting the object's motion. The terminal velocity can be calculated when the drag force equals gravitational force. This effect might have been more observable with an object that had a higher drag constant. However, most objects with high drag constants also have more profound shifts along the x and z direction when falling, which would have made accurate observation more difficult. There was also the influence of human error in dropping the ball and centering the mass, which could account for the differences between the observed and the drag force inclusive model. Overall, Newton's second law can be used to predict the motion of a falling object quite well, and accurately simulated the movement. Thank you for listening.